chemistry. And he stayed another year and he was also got a master's in history. From there, he went to Arizona and got a PhD in analytical chemistry, specializing in spectroscopy. Since then, he's been with us at AHS. Incredible asset. He's a great chemist, a geochemist. I'm really sure what they will do with that. We're all very proud of them. You go. Chris.
Thanks, Mike. Thanks, Amy. So let me go ahead and get the computer set up. So I'm going to commit one of the great sins that I've always been told to avoid of public speaking, and I'm going to essentially be tied to the podium. I will try to be more interactive, but I need to kind of be here driving the talk. So let me go ahead and set it up to share my screen. I think we'll go ahead and get moving from here. So this is, gave this talk earlier this year in Oklahoma City. If you caught it back in February, we haven't changed it much. We have fixed a few typos and added a few additional pieces of information. But this is really kind of a retrospective of what we've been doing in Oklahoma for going on, I think, something like 12 or 13 years now. So if we don't talk about your specific part of the scoop or the stack, I'm sorry about that. But this is very much focused on where we've been, who we've worked with, and what we've learned. It's a little bit tongue-in-cheek, as you might get from the title. 10 years running around the stack and the scoop. What did we learn extracting volatile subsurface fluids from all the cores and cuttings we could lay hands on and still run a business? If I talk like this, can people hear me? All right, I do not like this microphone, and I'm pretty good at projecting my voice. So we're just going to do it that way, because otherwise I'll just be standing here like this the whole time, eating an ice cream cone or doing something else. So let's just put that there. All right, great. And still run a business. So again, we're going to kind of be following where we've been, who we've worked with, who our friends are, and how that's taken us through the stack and the scoop. So I want to acknowledge two operators and the folks at those operators right at the beginning. Big thank you to Fairway Resources. No, they don't exist anymore, but still, we wouldn't be where we are today without them, especially Jeff Ice, who's retired. And big thank you to the folks at Ovintiv. I know they've gone through a number of changes, being Newfield and Encana, now Ovintiv. But many thank yous to Aaron Levitt, John Sinclair, who retired from Ovintiv earlier this year, Ovi Drezhnevek, Richard Brito, and Kinju. I'm going to show some supporting information out of Kansas today, so not all Oklahoma like the title promises, sorry. Just want to thank the Kansas Geological Survey for their help in putting together those supporting studies. So who are we at AHS? So we're here in town. We're just across the river. So we're very proud to be here today talking about what we've been doing out here. Company was founded by Mike, who gave me that kind of introduction. He got his PhD in geology from University of Hawaii, and if he got back up here, he'd proceed to make a bad joke about someone had to do it, so he went out there to take one for the geology team. After that, he worked at Anadarko Research for 10 years, which, if you're a Tulsa veteran, you probably have some memories of. While at Anadarko Research, Mike developed the first iteration of our technology, fluid inclusion stratigraphy. That, coupled with his experience, was pretty instrumental in the exploration and development of multiple Amoco assets. I'll go backwards in time, but hop forward a little bit, 99. We sell effectively the Generation 2 technology that Mike developed after leaving Amoco in 95 to ExxonMobil. That was called fluid inclusion volatiles. It addressed some pretty serious issues that the old FIS Gen 1 system had about crosstalk between samples, added some new capabilities. And as recently as, I believe, 2017 or 2018, ExxonMobil publicly stated at conference that they still continue to use that lab that Mike sold them in 99 as the first technology that new exploration wells are assessed with before deciding what follow-up technologies are going to be applied to the well. So pretty good for a technology from 95, still kicking around, pretty much unchanged at ExxonMobil, the better part of 30 years later at this point. So Mike worked with ExxonMobil at their upstream research company for a number of years, refounded the company in 2010. began developing our new technology in 2011. We call this Rock Volatiles Stratigraphy. It's effectively generation 3 in the development cycle. The two prior technologies really looked at fluid inclusions. And one of the nice things about sitting at ExxonMobil upstream research company in the early 2000s and mid 2000s, is Mike was able to see the upcoming advent of PDC bit cuttings. Those are death to fluid inclusions. If you take a look at PDC bit cuttings versus what we had in the 90s, 80s, 70s, or even earlier, you can just see the difference, right? We go from pieces that are actual rock to talcum powder. So trying to do any kind of fluid inclusion work on those PDC bit cuttings was not going to really be viable. Instead, what we've shifted over pretty hard to is what are the residual fluids from the subsurface still entrained in those PDC bit cuttings, although we can use the same technology just fine with older fashioned cuttings and core. So what we do at AHS, what we do this Gen 3 technology that Mike has pretty single-handedly developed, is we directly measure 40 plus volatile subsurface compounds that we directly extract and measure from the actual rock samples itself. You can see a breakdown of these here, C1 through C10 hydrocarbons, water, carbon dioxide, various sulfide species, various biological compounds, noble gases, stimulation compounds, and occasionally we even get some anions like sulfite and chlorides if the samples are particularly rich in them. We can do some work on isomers and isotopes. We pull these compounds out of the rock using a vacuum. We increase that vacuum sequentially, and that tells us something about how hard it is to get them out of the rock, and we can relate that also back to rock properties. We also measure mechanical strength by physically crushing the rock sample. So when you take all these direct measurements and put them together, it's over 120 different direct measurements of what is in the subsurface and how hard it is to get out. And that starts giving you, if you can imagine looking at cutting stratigraphically at 10-foot intervals in a vertical or 30 to 90-foot intervals in a lateral, a pretty detailed view of what's going on in the subsurface. And we generally use that work for oil and gas, but increasingly other applications like carbon capture, helium, geothermal. So just quickly in terms of how the technology works, we take the rock samples. We don't use very much. You'll see a picture of a sample holder in a few slides, but it's about the first digit of your pinky if you want to know how much rock volume we're actually talking about. And we just pull a vacuum on it. We don't use heat. We don't use solvents. If it's legacy material, we will crush it under vacuum. And we take those volatiles that we extract and we concentrate them on a liquid nitrogen cryotrap. So imagine a thin aluminum rod surrounded on the exterior in liquid nitrogen. The interior is integrated into the vacuum system, and you're just making a slurry of ice and hydrocarbon ice and sulfide ice and anything else that will freeze on that interior of the hollow aluminum rod that's exterior is being bathed in liquid nitrogen. Once you're done with making that ice, you just warm the cryotrap up, and the different compounds come off basically as a function of their boiling point, so pretty analogous to a distillation separation, and they'll pass to a mass spec. So here, this is actual cuttings data from West Texas, just showing you a subset. This is the mass spec response. This x-axis is effectively warming the cryotrap. And you can see first come off the butanes, the pentanes, hexanes, heptanes, octanes, nonanes, and a little bit of decanes. And these are all being monitored on their master charge channel. So it's not bulk mass spec like what you see with the mud logging teams, what you see with some of the other labs like the old FIS and FIV lab, the Gen 1, Gen 2. And there's some pretty unique advantages to having that separation step, whereas we warm up the cryotrap, things come off one by one. This is a nice example of it. We've been working on H2S a lot the last 3 years. This is H2S data from cuttings in a Haynesville lateral that came online day one with 100 ppm H2S. Again, x-axis is warming up the cryotrap. Y-axis is instrumental response on the mass spec. Each color is a different channel on the mass spec. This right here is your H2S. It's a pretty nice match to the reference spectrum. 34 is your dominant peak. That's the two hydrogens and the sulfur. 33 is a significant peak at about 40%. That's your sulfur and a hydrogen, and you cleaved another hydrogen off on the instrument. And then we have the +2 sulfur isotopic contributions at 36 and 35 for about the 5% sulfur +2 isotope. Here's the fun thing. If I didn't have this x-axis, if I wanted to make this identification just on 34 or on the whole fingerprint, I would have 1, 2, 3, 4 other compounds that would directly interfere with my ability to measure it. You're dealing with very high responses and you're on the rig. Obviously, there's really great H2S detectors that go looking just for H2S. If you are dealing with mass spec data and you don't have some kind of separation stage before the mass spec, and it doesn't have to be what we do, it could be a GC, it could be an HPLC, but if you don't have that separation stage before the mass spec, you're really going to have some meaningful questions about how sure are you measuring what you think you're measuring and how good is your quantification. So what do we use? I told you you'd see a little example of one of our sample holders. So 0.4 cubic centimeters of cuttings, core. I want you to keep that in mind. All the data I show you today comes from a sample that looks just like this. Here's a quarter for scale. We load these containers up. They go into our brass. You can see that this is sealed at the top with the nitrile septum. There's a polymer plug in the back. And what happens is that we will just perforate this with a syringe, full vacuum on it. And if it's a legacy material that wasn't sealed at the well site, we will also crush this radially with a 2-ton press while we're pulling vacuum on it. So we don't need a lot of rock. We can work with legacy materials. We can work with fresh materials. Pretty insensitive to the mud system. It's fun because you can work on really old materials, and we'll see some examples of that. The oldest we've ever done commercially are 1935 from the Cook Inlet, Alaska, and that was actively used to support an exploration program being run by Hilcorp a number of years ago. All right, so we do some of the best subsurface science you've never heard of. We do it every day. And a fun example of that, again, we're going to leave Oklahoma for a second, is understanding what the end of the world looked like for the dinosaurs at the KT boundary. So let's change this up a little bit. So if you ever go and look at 3D seismic in southern Louisiana, you can find these mega ripples at the top of the Cretaceous. These are tsunami debris flow deposits from the KT. So this is what looks like as the tsunami from Chicxulub comes on shore. We were very lucky to work with Dr. Kinsland at the University of Louisiana, Lafayette, so not LSU, but LU, Lafayette. And he happened to have a core from over here in LaSalle Parish that has one of these ripples in it. So this is the Midway Shift, this is the airfall, this is the mass transport, and this is the hard ground from pre-impact. And he just gave us a smattering of samples across this. What I'm showing you here is some of the data. Again, we're not optimized to measure things like oxygen, but we always measure it in every run. It's just kind of built in. And we found when we looked at just 34 kind of randomly distributed samples along that core that he had some really fascinating stuff. So for example, this is oxygen, this is CO2. You can see the arrows pointing in the directions. So we come up through the pre-impact chalk into the hard ground. You can see there's some changes in oxygen, but generally we have a baseline, right? CO2 is kind of sitting baseline. We come to the tsunami debris deposit. We can see that we start losing our oxygen. We can see that we're starting getting CO2. So this is the debris coming on shore. It's all being tumbled around. This is your snapshot of what the time zero right after impact probably looks like, you know, the first several hours. And then you get to the airfall up here, and now you're into the Midway Shale, which is time well after. And this is about 34 feet. Based on some depositional models, it's probably about 200,000 years of time. And oxygen just falls off a cliff and CO2 just rises like you wouldn't believe. And we don't have great sampling throughout this section, but right at the very top, CO2 finally kind of returns to something that kind of looks like baseline. Oxygen is still in collapse. So this is a really fascinating example of somewhat terrifying of what did the end of the world look like. And we're getting it from this data that we collect every day for oil and gas purposes. But in this case, we're looking at something very different. There's other interesting things in this data that we're not getting into. So for example, sulfur dioxide, which is this crimson line, takes off down here in the middle of the Cretaceous. This is probably the Deccan traps in India going off. You can see a little bit of a deflection in the oxygen as well where that occurs. So a lot of fascinating stuff in that data, really looking to expand that study. And I show that not because that's the focus of today's talk, but to, again, kind of show really just the amazing studies we get to do with this technology and the really fun things that we get to look at. So this study specifically, we went back, sampled that whole core a few years ago in Texas at the VEG. We're going to run it again, but after we purge all the samples with Krypton to get rid of air so that no one's sitting over there saying, oh, well, you're just measuring the ambient environment. So fascinating stuff, fun stuff, but we have to run a business. So how do you make money with this kind of data? Mostly we're working oil and gas. Increasingly, we're doing kind of carbon capture, sequestration, site assessments. We do some helium and hydrogen exploration and system analysis. Now, if you're working oil and gas, confidence is a big thing because I can show you a lot of curves, but if they don't relate to anything, what does it matter? So some of the things that we look at are water, how easy it is to get hydrocarbons out of the rock, which you would hope will relate back to permeability. And what I'm showing you here is some data from the Delaware Basin on the New Mexico side that we worked on in the late to mid 2010s. So where the technology is now is way better than where it was then, but it's still an impressive example. You take a look at the water saturation curve. The story behind this well is that the operator ultimately landed down here. So they completely missed their target in the Bone Springs. They made that decision based off of a completely different technology we weren't involved in. And they spent about $750,000 to do a pretty decent postmortem to try to understand what went wrong here. So this water saturation curve here, blue dots are from sidewall core analysis. Blue continuous line is petrophysics, water saturation. And then these red dots are our direct measurement of the water in these PDC bit cuttings 3 to 9 months after this well had been drilled. They're just sitting in storage. They give them to us. And this is pretty convincing, right? Everywhere where you see low water, we physically see low water in the cuttings. When you run into the water lake, congratulations, we can pick it out too. Over here, permeability, we're looking at how readily hexanes came out of the rock. Blue dots are sidewall core, green continuous line is petrophysics. Red dots are our ratio of hexanes coming out of the rock at 20 millibars versus 2 millibars. And again, this isn't as dramatic as the water saturation curve, but everything that says middling to okay permeability, we see it. Everything that says you start going tight, 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 we see it as well. It's not a one-off. We've done this kind of work in a number of different plays, including in the scoop and the stack. So we have some real confidence that when we tell an oil and gas operator, hey, this is going to mean something, it will actually mean something. So work in Oklahoma, it's going to be a little bit of a speed run going on this point forward. But we've been present in the state across conventional and unconventional oil and gas projects, the stack, the scoop, the merge, the Arkoma Basin, Marietta Basin, the Granite Wash, and the Oklahoma and Kansas border. We've also done some helium projects in the Keys Dome and Central Oklahoma. That work for oil and gas is generally petroleum system analysis, so looking at migration pathways, source rocks, both in multiple basins, the Anadarko, the Arkoma, and the Marietta. We also do a lot of exploration and appraisal wells at the beginning of evaluating is a play going to work. Do a lot of postmortems and completion design work as well. So looking at parent-child interactions in places like the merge and the scoop. I'm trying to just postmortem and understand why did a well underperform, a lot of that in the scoop and the Arkoma. And then quite a number of engineered completions in both the stack and the Arkoma. We've taken a number of those talks to conferences. What we're going to talk about today is we're going to start at where we began in the mid to late 2010s, looking at the Northwest Stack and understanding the role of lateral migration in the Mississippian limes. I'm going to go deeper from there into the Woodford and its role in vertical charging of those Mississippian limes. What happens when you go too deep, when the Woodford doesn't play well with structure? Can we talk about other things besides the Woodford? The Caney, maybe? And if there is time, which I'm a little worried there might not be, we'll talk about how do we deal with, this question of factory drilling, which has so dominated unconventionals in a place like Oklahoma, where you have 100+ years of oil and gas industry, which means decades of putting existing holes into the ground that might be trying to produce the formation you're now targeting with that lateral or might have impacted it. So kind of starting at the beginning of the story, we took a great talk to the Stack workshop at OU back in, I think this was 2018, with our friends at Fairway. And really, this was the beginning of kind of us getting to understand how we could use our technology to really go about looking at a petroleum system in a systematic way. So Fairway was very much in the Northwest Stack at the time. Key thing that defines this is that the Woodford is pretty immature out there. So you're really relying on conventional petroleum system stories to get that charge into the Mississippian limes, right? And what ends up happening is that faults are a pretty key part of that story. They serve as the hydrocarbon migration pathways. They are really key to controlling well placement in terms of, is that well going to do well or not? So we worked with Fairway to understand not just which faults were relevant, but what signatures were relevant in terms of the side of the fault that you wanted to be on, how much charging that side of the fault had received, And really that allowed for driving some interesting decisions about completion in their wells, but also how they wanted to use their acreage in terms of where they wanted to drill, where they wanted to not just drill, but even the trajectory of their laterals, which is really something you don't see in today's world. You're either controlled by stress field or you're controlled by land considerations. So this is one of the early wells we worked on them. It's 1 mile Mississippian lime lateral, and it kind of builds the entire story. What you're seeing here is a couple of different tracks. This orange track is water. This is formic acid, which is diagenetic compound. This is our permeability proxy. We kind of talked about that earlier from the Wolfcamp example, from the Bone Springs example in the Delaware. We have a couple of different chemistry compositions telling us about the potential for pay. We have this one right here, which is a migration signature. And then we have literally what are the volumes of the different types of hydrocarbons that we're looking at in the rock. These are legacy materials. They've been sitting in a warehouse for a few months before they come to us. When you think about that, good rock is going to lose its hydrocarbons the fastest, right? You think about going out to a road cut for the Woodford or the Eagleford or any other field trip you did with source rock. You dig into that road cut, you pull out the shale, it's nice and black, you crack it, you can smell it, you can taste it. It sits in the back of your car for about a week and it's gone gray, right? It's lost the hydrocarbons. So good rock should lose its hydrocarbons very readily. What we end up seeing here is that there's low water on this side of the fault. We see that there's high oil migration signature on that fault, this ratio of toluene to benzene. We also see that there's a very low resource in absolute terms on this side of the fault as well. And we see a number of charge signatures, which we're not going to get into. And all this kind of tells us the story that, okay, this side, which is the upthrown side of the fault, is where I want to be. And that is what has been charged. Coming over here on the downthrown side, we see a lot more water. So we're dumping brines into the downthrown side of the fault. We see that we do not have as good a permeability proxies. So those brines are dumping salts and causing calcite cementation. And we see lots and lots of hydrocarbons in there. That's not that it's not charged, but the fact that they're retained in legacy samples tells us they couldn't get out of the rock. And it just reinforces the story that, hey, this is tight rock. Fairway also did a lot of nice thin sections that show this whole section is full of calcite. So we know that the story is quite valid. This is not your good reservoir rock. Conversely, you charge this side because it's the upthrown fault block, and we have shut down diagenesis. And what you end up getting is a model something like this. If we imagine crossing the fault in a side view, you know, the lighter phase is going into the upthrown fault block, the upper fault block, the heavier phase of the water, those brines are going into the lower fault block along the length of that lateral. And so this obviously creates a situation where you want to be in this upthrown fault block that's been charged. And you also probably care about how far has it been charged. And this was allowed for a very simple engineered completion strategy on the part of Fairway, where they would go and they would say, okay, where we see good reservoir rock, we're going to do a quote unquote gentle frac. And where we see poor quality reservoir rock, we're just going to hit it as hard as we can. We know there's some resource there, and we just want to get as much of it as we can. And very simple engineered completion, but one that worked really well for them. A little bit about this migration signature that we're using here. Again, the nice thing about collecting direct data is you can go back and you can look at what other people know. In this case, if you look at literature from the 50s forward, whether it's conventional plays, unconventional plays, regardless of the source rock type, most oil and gas in the world, crude oil that's produced, has a ratio of toluene to benzene of about less than 3. This is some great work done in the 1960s by the U.S. Bureau of Mines that's demonstrating that with the profile of thousands of different oil samples. This line here is a ratio of 3, so you can see most of these samples are either on it or below it. You very occasionally exceed 5, but it's not common. And so that lets you set some thresholds to say if we see a value higher than 3, especially higher than 5, we're probably looking at a migration pathway. And again, that's how we justify saying that this fault is migrating oil, given that we have this discrete high of toluene benzene right there, well above 3. I have a little bit of science here, but just for the sake of time, I think we're going to have to hop through it. The key thing I want you to take home is that this signature works because toluene and benzene are both inflexible molecules, but toluene is just a little bit bigger than benzene with this methyl group hanging off the side of it. And so those molecules, as they travel through rock, toluene gets left behind preferentially because it's a bit bigger. It can't fit through all the crevices that benzene can. All right, so do all the faults in the stack work the same way? No, and this really makes direct measurement important. You couldn't just go out, do this on 1 or 2 wells and then model it. This is another well that crosses 2 different faults, and you can pick them out by this oil migration signature, but it's a much more complicated story than that first one I showed you, right? You know, what's being charged, what is the offset of charging, where's the good quality reservoir rock, where is the distribution of water? That's all very different and not nearly as pretty as that first slide made it seem. So actually going through and looking at these faults in each of these laterals was pretty important to understand where do we have the good rock, where do we have the bad rock, what's charged, what's not charged, how far away from that fault do we charge, and just even which faults are charging, because not every fault out here moves oil and gas. So that eventually allowed them to do something particularly out there, where instead of just crossing the faults and going perpendicular to the stress field, like most people would say, they actually started finding which fault blocks were charged, how far off from the fault, and they started drilling a few wells that looked like this, where they actually ran parallel to the fault in the charged upper fault block, and they had some great wells. You can probably, given that we're talking about Fairway, that we're acknowledging them, go look them up yourselves, but for the time, this pretty quickly let them start producing wells that out of an inventory of tens of wells, those wells quickly raised into the top 10, if not top 5 wells, as they brought wells like this online. So what did Fairway get out of this? The nature of reservoir quality, water content, and charge in relation to those faults was used in the planned engineer completions. And that was helpful to them. And they did do well as a business, but probably the more interesting thing they got out of it is they gave us 31-mile laterals across 2 counties. And you can imagine with 31-mile laterals all on the Mississippian line across 2 counties, pretty quickly you're making a very complete map of what faults are migrating, what side of that fault is being charged, how far is that offset of charging. And that was really powerful to them in future acreage decisions. What do we want to buy? What do we want to lease? Do we want to be on this fault, that side? And even well placement decisions like we talked about with those laterals. So work with Fairway led us to our friends at Ovintiv. At the time it was in Canada, that we're talking, to put this in context, 2019, 2020, right before COVID. And one of the things that Newfield had done before they become in Canada is they had collected a number of cores all throughout the state to kind of understand the nature of the stack play. At the time, Fairway had purchased acreage up here in Major County, what they call the Northwest Stack now, and they had specifically gotten access to this ABCDS core. So we took a look at that one, and there were a couple of interesting things that we saw in a vertical configuration. Some of this was stuff that we'd already known. So we saw, for example, this is our permeability proxy, high permeability at this Osage Meramec contact. That was attributed to like the protokarst development from subaerial exposure, so organic acids getting in there and just kind of starting to form karst, or at least protokarst in the Osage. We also see that we have high hydrocarbon liquids in the tree sections of the Osage. Again, this is the ABCDS core. It's been sitting out for 8 years during storage. This is telling us where the tight rocks are. The Woodford story was somewhat interesting to us. Very low hydrocarbon liquids are present in the Woodford, lack of generation, not necessarily surprising. Relatively low presence of aromatics compared to other Woodford samples that we'll eventually show, told us it was also immature. And then finally, the relatively high abundance of larger, more complex molecules, the C9, C10s, which are the most complex hydrocarbons we measure, again, kind of spoke to low thermal maturity, because those things should be cracking down once you start cooking the rock. In the relevant pay zone out here in the Meramec and Osage, really fascinating story, something you could probably only really see with core. Again, this migration signature right here immediately below the Osage and Meramec contact, right in the middle of the slug of high permeability. And so what's probably going on here is that's a very tight contact. You probably have literally just a few inches of migration conduit along that tight contact as you have oil just spreading and spreading and spreading because it can't penetrate the contact, at least not easily. That's inside this high permeability zone, probably the protokarst, and we can see that it's charged. We can pick out that charge on different signatures. So this is the ratio of benzene, toluene, ethylbenzene, xylene. You can see it actually looks like oil right here, so that tells us this section is charged. We can also see that the way water leaves the rock has been altered throughout this section where you have this green crossover. That means that the rock has become hydrophobic, water repulsive, most likely oil wetting. And that would fit with the story of reservoiring hydrocarbons here. So congratulations, we can pick out the zone. That's great. This is actually where Fairway was landing wells just a few miles down the road already prior to telling them this data. The other fascinating thing we saw on this core was our water data was getting better and better at the time. I already showed you an example on cuttings from New Mexico's Delaware Basin. But here, what I'm showing you is the water we get out of the rock easily at a 20 millibar extraction, effectively 1/50th of an atmosphere. The water we get out of the rock under difficult extraction at 2 millibars, effectively 1/500th of an atmosphere, in the sum of those. And then here's the petrophysics at the time that Fairway had put together. They only modeled the Meramec and the Osage, so they don't have a model that goes into the Kinderhook or Woodford. They just carried through the Osage model. But if you take a look at these curves, you start seeing that there are a lot of features from the petrophysics that seem to be repeating in the core measurements of water that we're making. If you interpolate the data points, because again, petrophysics says that half-foot intervals and our core samples are pretty randomly distributed. So if you interpolate the petrophysics to where we had core samples, you actually get a surprisingly good match of the patterns, right? So this is a really nice example of what our technology can do. We know that at least the theory and calculations, we know that the red track, the easily removable water, is water that's probably sitting in pores larger than 4 nanometers. This yellow track is probably looking at water that's in spaces of 4 nanometers down to 1.5 nanometers. And, you know, we're doing a good job of reproducing the petrophysics, but more importantly here, we can understand where that water is coming from. And that was something that Ovintiv was very interested in at the time because their petrophysical model of the stack showed a lot of water everywhere, but they weren't producing any of it. And this was something that their management was very concerned with. And again, you know, if you're not producing it, it probably means it's tight, but it's nice to have laboratory evidence that actually proves that. So we took all these studies from the ABCDS core to Ovintiv, made some great friends over there. Again, many thanks to Obi, many thanks to Aaron, Richard, Kin, John Sinclair. And we had the opportunity to work with them on the rest of those cores. And so we took those to a number of different studies. This is one that we took to ERTEC. And what we did here is we got all the other cores they had. And in this ERTEC study, we specifically wanted to look at the Mississippian and maybe how it was talking to the Woodford, but most of the focus was on the Mississippian. What we ended up seeing.
Duration of the project has continually updated our petrophysical evaluation.
Oh, hang on. I know what's going on there. I was very confused for a second. Sorry. So when I copied the slide over, I suspect what happened is that it's just continuing the recording that was built in. So now everything's gone a little wonky. What is this? Okay. So give me 1 second. I just want to shut the audio off. All right, there we go. So let's pick this back up. Okay. And so when we were taking a look at this, you know, the key thing that Ovintiv knew ahead of time was that in the Mississippian section, you know, very tight, very low porosity, but their petrophysics showed that the entire Mississippian section was fully charged, high oil saturation throughout the system. And yet that was somewhat confusing because mercury injection capillary pressure studies were showing in some of those samples that the petrophysics said were entirely charged. And were so tight they couldn't even take the mercury injection. So they wanted to learn a bit more about the system and overall. And additionally, they were already very happy with the water data we were producing. We're doing, in their opinion, better than the GRI method, which is kind of a standard method for core studies. And again, we were being able to speak very meaningfully to the lack of easily movable water. So we're going to unfortunately have to talk a little bit about organic chemistry. If you recall that from college, if you don't, it's fine. But when I talk about paraffins or alkanes, I'm talking about straight chain non-cyclic compounds. When I talk about naphthalene or cycloalkanes, I'm talking about cyclic compounds. And when I talk about aromatics like benzene, toluene, ethylbenzene, xylenes, I'm talking about these six-membered ring structures that are sharing bonds between them and are effectively flat like coins. So, give me 1 second. I'm so sorry about this. Let's see. All right, that should make it better. So one of the first things that we did is we just wanted to see literally what was the distribution of liquid hydrocarbons in all of these cores. You can see them broken out here. I've gone ahead and hung them all on the Woodford down here at 0. And if we zoom in a little bit, there's some things that become apparent right away, like how immature the Woodford is over here in Major County in the Northwest Stack. You know, we just really don't see any hydrocarbons on there. But as we continue to progress deeper and deeper into the Anadarko Basin, we do see that we increasingly have more and more hydrocarbons present in the Woodford. We also see more and more hydrocarbons present throughout the Mississippian. There's a few things that you can take away from the distributions. We already knew that very tight rock is what is retaining the liquid hydrocarbons. And so you start to see that these tight responses, these tight zones, have a lot of liquids in them. And again, that matches with the permeability, with everything else that was understood. We also see that there's a lot of gaps, right? You know, you can think of this as almost like a teeth on a comb. And these zones are picking out where you have better permeability, where you've been able to lose the resource over time during storage. There's something else that you get from this. The fact that we have all these high responses in tight rocks tells us that charging, so oil migration and charging, had to proceed in duration, because some of these rocks, again, are so tight that you can't get the mercury to go in them now. But our data is showing that those tight rocks are full of hydrocarbons. The oil saturation measurements from the petrophysics are showing that they're full of hydrocarbon. And this tells us that those rocks had to be charged before they were indurated, because if they were indurated beforehand, you wouldn't be able to push the oil in there, given how tight they are now. We come back to that idea of the comb with the missing teeth. Something else that you see is that most of these highs rise to the same level, right? So it's not perfectly bimodal, but you keep coming back to these similar maxima. And again, that tells us that we're charging the entire column at once. And again, it's just these tight zones that have done the job of retaining the liquid hydrocarbons in this pattern here. And again, this is all kind of building the story that, you know, we charged the system before induration, and that we charged it most likely in a vertical configuration with everything receiving a similar saturation. So how would we kind of take this and push it a little further in terms of understanding the charging story? We can look at the composition of the hydrocarbons. In this case, I'm showing you the ratio of those alkanes, those paraffins, so the non-cyclics over the cyclics like cyclohexane, so the cycloalkanes, the naphthalenes. And you can see that while there is some movement in these patterns, they're fairly consistent. So you can broadly use this as an oil typing metric. You can pretty broadly say that we have very similar oil throughout the entire system. And again, this just speaks to probably getting everything from the Woodford moving up in a vertical configuration. Again, this also speaks to pre-induration emplacement of the oil, because those cyclic compounds are very large. You are going to have a very hard time shoving them into very small pore throats if you've already indurated the rock before emplacement. And one of the things that really brings that home, I'm hopping around a little bit here, but I'm just trying to keep the story going at the time, is I can go ahead and take these different wells that we looked at. In this case, this is the state core, and I can look at the distribution of liquid hydrocarbons, right? And again, we get that teeth of the comb kind of profile, and we also see low zones. If I cross plot this composition, and again, this is paraffins over naphthenes, so when this value goes low, I'm dealing with more of those large cyclic molecules. When it goes high, I'm looking at, you know, a greater quantity of my alkanes, my kind of spaghetti noodle style molecules. Where I've lost more liquids from this core as it's just sitting around, if I look at the cross plot, I can see that I increasingly go towards having more napkins. And again, this just speaks to the fact that the resource had to be in place before we tightened up the rock. And not just the resource had to be in place before we tightened up the rock, the larger molecules already had to be present before we tightened up the rock, because as we've lost resource, these things are the only thing that sticks around. And that is because, again, they are now so large that they don't readily exit the pores as we cause the resource to evaporate away during storage. And all of this, again, just speaks to a story that at the time in 2020, 2019, and yes, oil is going negative, COVID's happening, we're all losing our minds, but Ovintiv was still very invested in figuring out in terms of what is the history of charge, especially in relation to when induration occurs. And all this data just seems to point further and further along with our petrophysics, with the mercury capillary injection pressure data, that charging occurred prior to induration. It occurred vertically, and it didn't happen along quote unquote highways. Nothing was necessarily preferred. The reason we would say that is here's that toluene benzene signature, right? Again, values greater than 3, especially greater than 5, would indicate significant migration. These are all scaled 0 to 10, and none of these have stuff just coming out of the Woodford screaming up the Mississippian. What does that mean? It means that we're charging continuously, but we're not on highways. So we're having a vertical charge that's not occurring in some places preferentially to other places, but everything's moving up in probably a very limited number of charging events, maybe just one charge. It's not that we're on a highway, we're passing volumes and volumes and volumes and volumes of hydrocarbons, like what I showed with those faults, but that the charging happens gradually in one push, not, hey, I'm going to move hundreds and hundreds and hundreds of additional volumes of oil through that rock, like what you see with the faults in the Northwest Stack. Okay, so going a little deeper, and I'm going to try to be a little more conscious of time here because I know that we've got about 15 minutes left. I'd like to leave some time for questions. Eventually, we came back and asked some questions about what's going on in the Woodford because most of the EarthTech study was focused on the Mississippian section. If you're not familiar with the Woodford, although I suspect everyone in this room is, you know, you've got the chert at the top, the siliceous and siliceous mudstones and shales, what Ovintiv at least calls the Woodford C and the upper Woodford. And then the Woodford B and the lower Woodford, we have the siliceous shales and argillaceous shales. And then in the very bottom, the Woodford A, the argillaceous shales and siliceous claystones. And chemist, not geologist, so if I butcher pronunciation, sorry about that. Looking at the distribution of different properties as these wells go deeper and deeper, you see some expected relationships. For example, here's the mechanical strength of the rock. Here's carbon neosulfide, its presence in the rock. And as we go deeper, while there's definitely dependencies on which subunit of the Woodford you're looking at, there's relationships that make strength. The rock gets harder as you go down. Go figure, compaction is a thing. Do you lose some of these sulfides as we go down? Go figure, they're less thermodynamically stable, they break down. Where this got particularly interesting, though, was the liquid hydrocarbon story. And again, that's what we're looking at here at these green tracks, the volume of liquid hydrocarbons. You can see the Woodford is this pink zone, is this kind of pink purplish zone here. As you take a look at the volume of liquid hydrocarbons we're getting out of these pores in the Woodford, it is increasing pretty steadily from the immature HCDS over in major counties as you come down to the Campbell. Something interesting happens, though. Once you hit the Campbell, you just start losing liquids somewhere around 10,300 feet TVD, and it's not really fair to think of it in TVD term because there is structure. You know, these are not just a nice transect marching its way down. But these three deepest wells we have, Rother, Williams, and Mashburn, they're completely off trend. They have no trend relating to generation. You don't see the nice bell curve that you see in all the textbooks where, okay, we start cracking, so we're going to gas. You just have kind of a loss that looks to be somewhat haphazardly distributed. Now, the volume of water is decreasing in each of these, which is what you would expect. You know, you have compaction, so you're using pore space, you have more generation, you're cooking the rock. So yeah, we should be losing water. Why are we getting these weird distributions of hydrocarbons, though? One of the things that we looked at is another migration signature. So I talked about that toluene to benzene one. I talked about that a little more chaotically than I'd like. But you can use these small molecule ratios to understand how things move around. One that we use is what we call pseudo B. It's the relationship between toluene and heptanes. It's just the ratio. It's based off some work that Keith Thompson did in the 1980s, where he was able to use that ratio, toluene to N-heptane specifically, to look at gas migration in the Gulf, in the Williston, Alaska, a number of other places around the world. Value goes high means that you moved gas through and stripped out the light condensate that could go with that gas. Value goes low means that you probably just found in-place condensate. Again, it's pretty nicely driven by the properties of those molecules in relation to how soluble they are in a gas phase. And again, I'm skipping ahead a little bit, try to make the time that we have work. This is on a log scale. We're covering 4 orders of magnitude with this pseudo B track. And you can see most of these as we go from ABCDS, Johns, Yost, Campbell, are coming in at this first marker right here. And to the extent the number matters, this is about 0.03 to 0.3 is where these guys are coming in. You come over down here to Rother, Mashburn, and Williams, and you start seeing discrete responses. So again, this kind of sawtooth pattern where you are 2 orders of magnitude higher for this gas migration signature. And so this would tell us that we have discrete zones in these Woodford cores where we have lost gas, where we have evidence of gas moving out pretty significantly. And if you start taking a look at the cross plots of things like the volume of liquid hydrocarbons that you're measuring versus that pseudo V ratio, there does appear to be a pretty meaningful kind of 1/X relationship. So this means that those liquids that we're missing from those pores in the Woodford that should be there, that we should expect to see there, those were probably migrated out by some gas-mediated process. And there's 2 ways you do that. You could either do that by self-expulsion, so you lose gas, and it carries its own liquids away, or you could bring dry gas up from below and try to move that through the Woodford. Now, given the distribution of these patterns in the Woodford, I'm going to immediately say I don't think that bringing dry gas up from below and trying to move it from the Woodford makes any sense. You know, you don't see any particularly higher responses at the base than the top. This looks probably like self-expulsion, that we are losing gas preferentially at different points in the Woodford, and that's carrying our light liquids along for the ride. You can kind of further build out that story if you look at the ratio of the paraffins, so the more thermodynamically stable molecules, versus the naphthalene, less thermodynamically stable molecules, so the cyclics. The heaviest liquid hydrocarbons that we measure, the C10s, you get this nice kind of curve that matches what maturation should look like. You crack those cyclics and you go on an alkane paraffin-dominated trend. You don't see that with the lighter hydrocarbons like the C6s. And again, this kind of suggests that those lighter liquids are being preferentially lost due to this gas migration process. You can, again, cross-plot a lot of different parameters to build out the story that says as we lose liquids, it's because we're going to higher pair, it's because we're having more of this gas migration signature, and that what is left behind when we lose liquids is increasingly the smaller, what is left behind as we increasingly lose these liquids is the larger hydrocarbons, the ones that are going to be less mobile in gas. So at the end of 2023, when we're doing this study, you know, someone at Ovintiv pops up at the very end and says, hey, you know, those 3 wells are right next to faults and fracture networks. You know, could that be providing the pathway out for the gas? Yeah, probably, especially when you take a look at some of the other work we've done. So over here in the Arkoma Woodford, this was some work we did for Bravo a number of years ago. They kept running over these massive faults in the Arkoma Woodford. And they had a very basic question. Does this affect the petroleum system? Yeah. Here's one of those wells. You can see as it runs over some of these massive faults, we start losing gas and liquids pretty noticeably in relation to those faults. So yeah, if you have faults, if you have structure in the Woodford, that can very much serve as a thief to take away your resource and give you a conduit out. So we went back to that Woodford study in 2025 this year. We pulled the production data from all those cored wells because now most of them have been turned into producers and turned on. The completions differ in features like choke sizes, and that makes direct comparison of gas or oil production difficult. And additionally, some of these are just completed in the Mississippian, not the Woodford. However, API gravity and initial shut-in pressure shouldn't be affected by things like choke size. And API gravity is going to function as a good indicator of evaporative fractionation. That's this gas migration process where you take the lights with the gas and increasingly leave the heavy behind. If we're looking at something that's lost its lights through that process, it should be a heavier resource. If we're looking at something that's gained a lot of lights through that process by emplacing condensate, it should be a lighter resource. What we find when we look at the API gravity of those wells, and again, take a look at the key here because these are not all Woodford, is that as you go deeper, you have a trend that you would reasonably expect, right? Where we're getting higher and higher gravities because that's what maturation should say. Right around when we get to Rother, which is what these red dots are marking out, some of these are from the Rother well, some of these are from parent wells that are within 1 or 2 miles of the Rother well. We break the trend. So our Mississippian wells just go off, you can see to the right. They no longer care about depth in terms of their gravity. Their gravity seems to be responding to something very different. And as we look at the Rother and the deeper Woodfords from the Williams and the Mashburns, our gravity is no longer linked to depth either. And so if you think about a gas expulsion process that carries the hydrocarbon liquids with you, this makes sense. You're going to be losing your lights, your 5s, your 6s, your 7s, your 8s, as they are carried away by gas that is traveling along faults and fractures as a secondary expulsion from the Woodford. At the same time, what you're seeing, especially with this well right here, is that has to go somewhere. Conventional petroleum systems still matter. Sometimes that condensate is being redeposited in the Mississippian, and that's what we're catching with this one Rother Mississippian well over here. So that's the API gravity. Pressure should follow a similar trend. It does. Whether it's the Mississippian or the Woodford, we see it nicely increasing with depth up until we get to Rother, which again is where the core for the Woodford goes off trend. You can see once we get to the Mississippian wells around the Rother well, we start increasing pressure in a way that does not relate to depth. Again, if you think about migrating gas, carrying condensate, getting in place and trapped in the Mississippian, this makes sense why you would get higher pressure. Conversely, if we look at the Rother Woodford and the deeper Woodford, we no longer seem to really care about going down and getting deeper. And again, if you think about gas expulsion, gas is going to be one of the main drivers of what you and I think of as pressure, right? Pressure is just the number of molecules physically hitting a surface. What's going to be the most dominant set of molecules you have that physically pound into that surface? The gas molecules, the methane, right? So as we've lost gas in the Woodford, that's why we're going off the pressure trend. That's why we probably don't seem to care anymore about the increasing depth, is that as we increase depth, guess what? We just expel more gas into these fractures and faults, and we start alleviating that pressure. What did Ovintiv get out of this? Because it's a really fascinating story. I probably haven't done justice to it because I'm up here trying to speed run through the better part of 50 slides for an hour-long talk with some technical difficulties. So what Ovintiv turned around and used this data for is they were happy to understand the petroleum system. But one of the things that this let them do pretty quickly was make operational decisions. So they took the water data, they took what was the hydrocarbon data. Water obviously is just telling us where there's more water, how movable it is. Hydrocarbon data is a little more interesting. It's telling us not are there hydrocarbons here, they already knew they were fully saturated from the petrophysics, but where is the rock that it leaves the most readily from, based off of how much we see versus how much is lost. And you can use that data to say, okay, this section we have high water, high hydrocarbon responses, so we have tight rocks with high water. Conversely, this section, low water, low hydrocarbon responses, good rocks, low water. And they actively use this data in a form pretty similar to this, from what I understand, to drive well placement decisions for the next several years in relation to where we provided this core data in the surrounding areas. There's more that I would like to talk about today, but we are right at the edge. We're at like 12:57. So if folks want, I'm happy to talk about the Caney, and I'm happy to talk about parent-child. Conversely, we're not at a bad place to end the story talking about the Woodford and the core study we did with Ovintiv. So people want to hear about the Caney and parent-child, or should we kind of pull it off here? And again, I'm sorry that I'm not handling the time well. Caney? All right, let's go to Caney. So again, Ovintiv, great friends. We love them. They usually let us take what we do and publish it within 1 to 2 years after doing it. So in 2020, 2021, people are busy trying to figure out the Caney quite a lot. That includes Ovintiv. They give us a series of wells drilled not completely right on top of each other, but effectively you can think of it in the same lease or the same pad. It's not quite true, but go ahead with that. And what they had done is they put a lateral into the Mississippian Caney and they put a lateral into the Woodford. Again, these are not perfectly on top of each other. They're somewhat displaced. They were interested in a couple of different things. Both of these wells encountered the same faults. You can see them here. So they wanted to know what those faults were going to do to the system. But they were also very interested in trying to figure out, is the Caney going to do better than the Woodford? Or at least how well is the Caney going to do compared to the Woodford? Should this be something that we really target as its own bench? They used two different types of samples that we have. These ones where we seal the sample at well site. Unlike the core study I just talked about, this is a really nice X marks the spot style approach. So it gives you a very good sense of how much hydrocarbon is there, what the representative composition is. This is also the sample type that we used in that Woodford Oklahoma example I showed you, where you just lose the gas and the liquids in relation to the faults. And then they also took those same samples and just let them air dry. So we're not using heat lamps or anything. We're just sitting them out for a couple of weeks. Everything that can leave leaves the rock. And the value of that is it's what we get our water data from, but it's also a very good sense of reservoir properties in terms of what lost the resource more readily. Just in terms of comparing the Woodford versus the Caney, there was a couple of interesting things we did here. So if we take the liquid hydrocarbons that we see in the sealed samples as our ground truth, how much resource is in the ground right now? And yes, there's going to be losses during production coming to surface, all these things. But if we say this is representative of the resource in the ground right now, we can see that the Woodford has about 50% more resource in those cuttings than what we saw in the Caney. We can also, again, let those cuttings dry out and see how much resource is still retained in them. We see that the Caney loses something like 53% of its resource, but the Woodford loses something like 75%. If you go ahead and drive those numbers forward, that lets you start making some interesting predictions and statements. The first statement that you'd make is, okay, the Woodford has more resource and it gives it up more readily than the Caney. But these wells were actually completed virtually exactly the same way. They're at the same length. They were completed within days of each other using all the same completion schemes. So really you have an interesting case here where geology is actually your control. And so we were able to do something a little more interesting than just saying, oh, we think the Caney is going to underperform compared to the Woodford. We were able to push this forward in terms of just doing some really basic math here. You can see the calculations that we're doing. We're just looking at how much liquid is in one formation versus how much is lost from that formation. And we can compare that between the two different wells. And we can make some predictions about, if we pulled the resource from both these laterals, how much do we think each would contribute? We thought that the Caney would contribute about 32% of the pulled production versus 68% from the Woodford. 2 years later, with the real numbers, the Caney contributed 39% versus 61% of the Woodford. But pretty good for a back of the napkin calculation that didn't involve thinking about stimulated volume or anything else. So we could have definitely firmed up that number. But it was a nice way of just understanding that not just the Woodford was a better rock in terms of reservoir properties and the amount of resource there, but even kind of trying to add some real numbers in terms of how much we thought that bench was going to outproduce the Caney in a way that was pretty meaningful at the end of the day. So the next bit is parent-child relationships. This is pretty quick, but we're at 101 right now. Do we want to look at this, or are people just kind of, I see some heads nodding. We'll keep going. If people just want to start leaving, my apologies. This is just 3 slides. So there's a lot of existing holes in the ground in Oklahoma. That's not a new thing. A lot of them have been stimulated. Not all of them have been stimulated. You have plays like the Hawks Bar and the Maze Carbonate and others where people have gone down to what is now the unconventional target, but in the 70s and 80s did it with a vertical and stimulated it, right? I'm showing you an example from the merge where we're looking at 2 2019 laterals that are landing in the same carbonate. We turned this data around in 2019, so the operator actually used it. We have what we're going to call east well and west well. These take different landing pathways down, but once they land, they are in the same rock the same way. The geosteer purposely wanted them to parallel each other. The big difference between east well and west well, the east well comes within 300 feet at the point of closest approach of an old 94 borehole. Today it's plugged and abandoned, but it produced for about 25 years, and it stimulated and produced the same carbonate that these laterals are landed in. When you take a look at the data, this is the mechanical strength. Again, we're getting this by just physically crushing the rock sample. And it tells us that once we land, broadly, we're looking at the same rock. The patterns match each other. Great. Laterals parallel to each other, just like the geosphere operator wanted them to, and the gamma ray says. This is CO2 right here. CO2 is very interesting for us because if you look in the literature, this is actually, its presence in the subsurface is principally controlled by what you and I would think is reservoir pressure. Whether it's a water phase or an oil phase, its solubility is highly linked to what you and I would think is reservoir pressure. Initially, again, they take different ways down to land. Once they land, very, very similar CO2 profiles until about the last 1,000 feet of the east well. We just lose somewhere between 3 to 7 times the amount of CO2, depending upon where you want to say that baseline is, in the east well versus the west well. Now, what happened here? Well, this just happens to be dead center in the middle of that 1,000 feet on top of where we come to that point, the closest approach to the old 94 borehole. Won't go through this whole story, but what I'll tell you is to prove this, we went over to Kansas, got a whole bunch of DSTs, and showed that the ratio of CO2 divided by water, which is probably the phase they were dissolved, the CO2 was dissolved in, matches very linearly to initial shut-in pressures from DSTs. So yeah, there is value to using CO2 as a proxy for pressure in the reservoir. If we take a look at the east well, what we can see is that as we come to that point of closest approach, 2 discrete liquid hydrocarbon responses, and what fractures that connect our data. So these are probably stimulated fractures from the old 94 borehole. We can see that those fractures are different than other things in the well. They've changed how readily the water releases from the rock. So again, some indication they're artificial. They have tons of organic acids in them. We have 3 other wells in this study, so we know how much organic acid is normally in the rock. These are microbes. Microbes have invaded these simulated fractures from the offset borehole. When we come here, we lose the CO2. It's discretely high here, probably because of what the microbes are busy making. And so all of this would tell us that congratulations, it's not that we don't have resource, but we've definitely lost pressure across this 1,000-foot section of the lateral. And that's mostly been stolen by the old 94 borehole. So we turned this around, told the operator decided to leave it as a duct. New operator came in after COVID, decided to turn this one in the west well on, and go figure, when you go and look at the initial production reports, east well had 1/3 the GOR of the west well. Again, if you want to think about what controls pressure, the number of molecules in the subsurface and how hard they're hitting a surface controls pressure. Gas is going to control pressure. Now, we can't do a direct comparison of pressure because they use different choke sizes. But what I can tell you is that in the case of east well versus the west well, even with a significantly smaller choke size on the east well, 28 versus 34, the east well still had a significantly lower flowing pressure, 820 psi versus 1,200 psi. So in terms of making a prediction, having an operator listen to you, and then having the next operator say, I don't care, I'm turning them on, we feel pretty good about the value of that predictive capability in terms of, yes, there was lower pressure. And while they don't have the same choke size and they don't have an initial shut-in pressure measurement in the released state reports that IP points to, I can point to the difference in GOR and the difference in flowing pressure, even though the choke sizes are different, to show that, yeah, the east well did have significantly less pressure than the west well. And so there was value in telling the initial operator, hey, I don't think you really want to compete with the east well. It's going to underperform. All right, this ran way over, and I know I speed ran through a lot of this. So thank you all for sticking around. I see that I got a lot of your attention once I started talking about expelling gas from the Woodford. So I'm glad that it clicked and people were liking some of the story at least. Oklahoma's our home. Tulsa's our home. Our lab is just across the river. A bit farther, a bit away from Chandler Park. So we're very proud to be here. I keep apologizing for the speed run, so I'm sorry about that, but I am very proud to show you guys what we've been doing in Oklahoma in the last 10 years. Forgive me for talking about the Delaware, and forgive me for talking about Louisiana, Kansas a little bit, but we're pretty excited about the work we've done in Oklahoma, and we keep doing wells in Oklahoma. So see you all at MidCon. You get to hear about some more Oklahoma studies then. Thank you all very much for your time. Yeah, and I know this was a lot to take in, and if someone came here just like, hey, I want to hear just about the Woodford, or I just want to hear about parent-child or Caney, and you got stuck hearing about how up in the Northwest stack, the faults are important for charging the Mississippian, I'll just say thank you for doing it. Yeah, I know that some of this ended up being a speed run, so I hope the story makes sense. If it didn't, or if you want to know more, I'm in town all day today. I'm going to be in town most of the day tomorrow. I'm probably going to go to Oklahoma City or Wednesday afternoon, Thursday morning. But reach out to me, reach out to Mike. We are here in town. I live in Midland, but Mike's here in town, and I'm in town for today and tomorrow. So we'd love to chat with you guys. We'd love to share with our local community what we're doing, and we're always looking for new partners and new folks to work with if they got interesting questions. Thank you all very much.
Thank you. I will break down. I just stick around and that. I'm trying.